Thanks. All right, hi everyone. My name is Katie Lester. I'm a postdoc at NASA Ames, and I did my PhD from Georgia State in 2020 doing orbits of binary stars with CHARA. So I was asked to give a review of binary star science with interferometry, which is a very broad topic. So I'm only gonna, well, my goal was to try to highlight some recent observational results and science goals that we're working towards with interferometry. So I'm sorry if I can't cover everything. These are just a few of the many many science goals we can cover with interferometry. Okay, so I'm going to start just going over some of the basic observational background for anybody who's maybe new or doesn't do binary stars. So for binary star science, you can use either speckle or long baseline interferometry. Typically, if you're doing speckle, you're limited to just measuring orbits of these stars, typically the wider binaries, since the angular resolution is only about 50 milliarc seconds, since you're limited to the diameter of the single telescope. But of course, to do the smaller, shorter period binaries, you need to do long baseline interferometry and get down to the milliarc second regime. And that allows you to look at the orbits of these close binaries, doing angular diameters, doing imaging of, as we've seen, disks and interacting systems. So can probe more of the binary environment with long baseline interferometry. So the first type of modeling that you can do, of course, as we've seen, is doing fitting the visibilities and the closure phases to get the astrometry and the binary positions and the flux ratio for your stars. That's, of course, what you need for the orbits and if you're doing the angular diameters. So on the left is a visibility curve for just one baseline. So for binaries, of course, you see this like sinusoidal pattern. And then on the right is the example for a UV plane. You get these like broad stripes that their separations tell you about the binary separations and how far down the visibilities go, tell you about the flux ratio of the binary. So this is some real life examples for a couple different baselines from CHARA data. So you see for each baseline, you kind of get pieces of this sine curve that you can use to fit for the binary positions. These are some examples of the closure phases. They're a little bit less intuitive, but typically for equal mass or equal brightness binaries, they'll jump from 0 to 180. And then as you get to fainter companions, that jump kind of smooths out and you get, you won't go all the way up to 180, you'll get smaller closure phases. But as you can see, you kind of get these little arcs for the binary systems, depending which triangle you're looking at. And then if you're doing more complicated things, of course, you would do more of the imaging. If you have more UV coverage to allow you to reconstruct the images of the binary and the environment around the binary. This is, as we'll see, when you do more interacting systems in the disks, this is where imaging comes into play. So this is an example of some visibilities for binary system made up of two very, very young stars with circumstellar disks around them. So you can see the large scale variations, kind of that same sinusoidal pattern from just the fact that it's a binary. And then you get some smaller, more complicated structures from the disks around the two stars. So once you have all of your observations, kind of the most basic thing you can do with the binary is to measure the orbit. So we're going to look at a bunch of orbits for the next few minutes. From interferometry, you get the visual orbit, as we've seen some examples already. Measuring the position of the secondary star, watching it move around to the primary star on the plane of the sky. And then when you combine it with the spectroscopic orbit, you get the masses and the distance to your binary system. And apart from getting really accurate stellar parameters, this doing binary orbits with interferometry is important for connecting kind of different spatial scales of different observational techniques. So connecting kind of the very short period, really close spectroscopic binaries from like rate of velocity surveys to kind of the wider binaries that you would do with more traditional imaging surveys. You can kind of connect those spatial scales and overlap with binaries that you can observe with both of those methods. So these are some more examples of binary orbits. They're all, they look very similar. Declination as function of the very ascension. You'll see again, the positions of the secondary star plotted with the elliptical uncertainties and best fit model orbits. So a lot of times the uncertainties are much smaller than can be plotted on the data, or much smaller than the size of the orbit itself. So with this really precise astrometry, you can see, for example, a triple star system that on the left is a plot of most of the historical data in the black circles, just mapping the position of the secondary star because they thought it was a binary. But then when you observe it with the chara with really precise astrometry, you can see that the secondary star is actually wobbling and is in fact a triple star system. And you can map out the orbit of all three components. And as you can see, the error bars are much, much smaller, and you would not even be able to see them on the plot on the left-hand side. So when you get the binary distances, this is important for comparing these independent distance measurements to other distance measurements like trigonometric parallaxes. So this is an example, a couple stars that would observe with Hipparcos in their visual orbits, and then getting really precise distances with 1% uncertainties at most. You can plot up the distances, from the visual orbit called orbital parallax on the y-axis, and the Hipparcos parallaxes on the x-axis. And for these systems, they're pretty consistent. As you can see, they're much smaller error bars for the orbital parallax than from Hipparcos. These are some examples compared to Gaia parallaxes. So one visual orbit on the left, and then the orbital parallaxes versus Gaia parallax for a few systems in the right-hand plot, and then the residuals on the bottom. So some of the stars fit, some of them don't. So there's a lot of systematic errors still in the Gaia parallaxes, probably because they didn't account for it being a binary. So you have to be careful. It's good to double check these things, but also best if you can measure the distances independently and not have to worry about any systematic errors. Moving another step on the distance ladder, you can look at the period luminosity relationship for Cepheid variables. So this is an example measured with chara, looking at the visual orbit and on the left, and then plotting the star on the period luminosity relationship on the right. So I believe the star they looked at are these, the red and blue points. I think the red points were, if you don't account for the light from the companion, it doesn't quite fit, but once you correct for that light from the companion star, the Cepheid falls right along the period luminosity relationship, which is great. But observing more of these with really precise distances will help kind of nail down, for example, the 0 point in this relationship better than looking at some of these other stars with much larger uncertainties. So again, really important to calibrate all the different rungs of the distance ladder, since they're going to propagate outwards into all other areas of astronomy, stellar and extragalactic astronomy. So we want to make sure that we're doing the best we can by comparing them to the binary distances. So the other thing, of course, you get the binary masses with really great precision when you combine with spectroscopic orbits. So this has been done for most stars that have visual orbits, as we've seen already, but this is just one more example of a pre-mean sequence binary system. So again, visual orbit on the left, and then in comparison with some Dartmouth stellar evolution models on the right. So these black lines kind of going up to the left are the isochrones for different ages, and then the gray / blue kind of vertical lines are the evolutionary tracks falling onto the main sequence. So you can estimate the the age of the system, probably about 3 million years. And this is important for, one, making sure that our models can accurately predict the parameters of stars for different ages and help test the physics that goes into these models, but also learning more about star formation and getting ages and accurate, well, ages and distances for star forming regions or living groups, things like that. Okay, so Gail mentioned this yesterday, but we're gonna look at it again anyway. So moving to the other end of the evolutionary sequence, it's important to get masses of very evolved stars. So this is, again, the orbits and visual and spectroscopic orbits for Wolf-Rayet star. So these evolved stars that are have kind of blown off their outer envelope through very strong stellar winds, and getting dynamical masses for them is very important to see, how much mass got blown off in the wind, how much mass is left to possibly, form a supernova progenitor through core collapse. So getting accurate and precise masses for these stars at the end of their lives helps really nail down the evolutionary sequence, especially from these massive stars. I know I'm showing orbits up here, but if you don't have enough points for orbits, you just look at a few stars, maybe once or twice. Interferometry is really important for multiplicity surveys. So this is an example, 2 different examples of papers that look for companions around BE stars. So again, these BE stars, one of the popular information theories is that the companion evolved and donated mass to the B star, which got spun up and then spat out some of the material into this disk. So if that's true, all BE stars should have companions, but there are these subdwarf companions that lost their outer atmosphere. They're very faint in the optical and the near infrared. They're really only bright in the UV. So it's very hard to see them, but thankfully interferometry is really good at looking at faint companions since we have such precise closure phases. So both these papers were able to look for known and unknown companions around B stars, and we're successful in finding many of them and help kind of supporting this theory, this binary formation theory for BE stars. Again, I know I talked about this yesterday, but it's a great plot, so we're going to look at it again. This is an example of looking at companions and multiplicity rates for very massive stars. So here we're filling in this very top part of the of this multiplicity fraction versus mass plot, and looking at it, I think interferometry was used in most, if not all, of the other data points on this plot, since again, it's great at kind of tying together different spatial scales. So looking at multiplicity rates is important for testing star formation theories and doing orbital demographic studies. So especially as Emma mentioned, for these massive stars, looking at different formation pathways and helping to constrain which methods result in such a high multiplicity fraction. Okay, so moving slightly away from the orbits, going on to more of the imaging and moving out from stars, more of the binary environments. We're gonna look at some of the same types of stars, but doing more of the imaging. So coming back to BE stars, this is, I think, a famous plot of reconstruction of the BE star. You can see the BE star in the middle with its accretion disk around it, and then the positions and the orbit of the subdwarf companion around the outside. And again, this is important for, looking at if the BE star disk and the companion's orbit are aligned with each other, and they are, so that helps support this theory that they're physically connected to each other, that the companions help form the B star disks. So if they were completely unaligned, that wouldn't support this theory. And then the plots on the right show the B stars disk at different wavelengths. So looking at gases moving at different velocities. So, the blue shifted side of the disk versus the red shifted side of the disk, mapping the rotation and some of the structures within the disk, trying to learn about the disk evolution and some of the physical processes in the B stars disk. This is another example for B stars. So the top row is CHARA data looking around the H alpha emission line. Bottom row is VLTI data looking around the bracket gamma line. The first column here is looking just at the continuum. So you're mostly seeing the B star itself, and they were able to resolve the B star and get the physical radius of the B star. And then the second column is just looking at broadband data, kind of looking at all the light. And then the plots on the right, kind of onwards, are looking at different velocities. So again, looking at the red shifted and blue shifted side of the disk and modeling the rotation, modeling the kind of the physical sizes of the disk. And this is important to compare not just the sizes at different wavelengths, but compared to other BE stars that have been observed, trying to see if there are any similarities, if they can kind of try to learn about BE stars as a whole. Comparing the extent of the disk at different wavelengths is really important. So hopefully we can observe more BE stars in different wavelengths to try to see, try to nail down kind of the radiative processes within the disk. So this is an example of an interacting system. Again, visual orbit is on the left, and then a little movie of the reconstructed images is on the right. And this always confuses me because it looks like it's going backwards, but it is going like up to the left as it goes around. You can see, especially when it's kind of in the corners of the orbit, the companion does have like a reverse lobe shape. It is a little bit distorted. So you can see the evidence for mass transfer or past mass transfer within this system. This is another example of an interacting system. They did cover the whole orbit, but this is just kind of one snapshot reconstruction for the specific orbital phase. You can clearly see the Roche lobe filling star transferring material onto its companion and the accretion disk. So this is like pretty much, it's a reconstructed image, but it looks just like a textbook image, which is really amazing. And also some evidence of a hotspot on the accretion disk, maybe due to the material like actually transferring onto the disk, maybe just due to reflection from the Roche lobe filling star. But it's great to be able to actually see different structures within the disk and look at, mass transfer in action around these stars. Whoa. See, now mine got messed up too. The GIF is there, that's the most important part. So this is an example of a Wolf-Rayet star. Again, the ones with the very strong stellar winds. And for this system, the wind from the Wolf-Rayet star was colliding with the wind from its companion. And there was dust forming along the shock front that then gets blown out of the system by the wind from the Wolf-Rayet star. So then as the two stars orbit, the dust kind of follows the spiral pattern. And all of the reconstructed images were in that plot in the top, but they're all in this little movie on the bottom. So I think several Wolf-Rayet stars have been observed to have the spiral pattern like this, which they can use to look at the shape and kind of roughly estimate if it's a circular orbit, which is evidence that there was mass transfer in the past that circularized the orbit, and use reconstructed images like this to study the wind interaction between the two stars. So this is an example of a circumbinary disk from VLTI. The let's see. If you look on the right-hand plot, the primary star is this blue star on the top left, and the secondary star is this green one on the bottom right. And then you can see the circumbinary ring here. And they also found that there was a circumstellar disk around the secondary star. So for this very evolved system, that mass was kind of blown off the primary star, and it seemed to be accreting around the secondary and forming this ring around both stars. And I know we're going to hear more about them later, so I'm not going to talk about this too much, but still some very cool images coming out of circumbinary disk in the evolved star field. Okay, so just to conclude, again, I'm sorry we couldn't cover everything in a limited time frame, but I think the most important things to remember is that there's a lot of recent technological advances that have really helped, well, all fields in stellar astronomy, but specifically binary stars in a big way, having more baselines, longer baselines, different wavelength coverage that allows us to get better UV coverage, yields really precise astrometry, micro arc second precision. So you get really accurate orbits, really accurate stellar parameters, such as the mass and the distance, and technology upgrades, getting more sensitive instruments with really precise closure phases allows us to detect binaries with very faint companions, a few percent of flux that you probably couldn't see using most other observational methods. And this really allows us to image the binary star environments, look at binaries in different evolutionary stages, look at these substellar companions that are very, very faint. So it opens up a lot more binary systems for that are accessible to interferometry. So really quick, just plotting some of the things I talked about on the HR diagram. You can see they cover pretty much all of the HR diagram except the white dwarfs. And I've only mentioned a few things. We've covered orbits pretty much all the way down the main sequence, a lot of orbits up at the giant stars. So this really wouldn't be possible if we were just looking at orbits of main sequence stars. We wouldn't be able to learn about evolution all the way around the HR diagram. So again, if you remember anything, just remember that we're able to get really precise orbits and stellar parameters. We're able to open up studies to all different kinds of binary stars and interacting systems. And this really has allowed us to connect binary star evolution to stellar evolution and study systems all around the HR diagram. So that's, I think, the most important part. So thank you very much for listening, and I will try to take any questions. So if any of the PIs are in the audience, feel free to correct me if I'm wrong.
Thank you for the excellent review, Katie. Are there any questions from the audience? While you're thinking, maybe I'll ask the first question. So you mentioned the pre-main sequence stars at the beginning of your talk, and I started wondering that in recent years, one of the smoking guns of recent star and planet formation studies was the direct detection of protoplanets still embedded in their disk, in the protoplanetary disk.
Mm-hmm.
But these were direct images. So I was wondering what do you think? Will it be possible to detect these kind of protoplanets with an infrared interferometry like VLTI or perhaps CHARA?
I mean, I think we have detected them with VLTI. I'm not sure if we have enough contrast to see them with CHARA. Not sure, but yeah, that's really interesting. They're very, very faint.
Question. Yeah, that's why it's so difficult. Any questions from the audience? Okay, then let's take a question from online.
Sorry.
Is the binary observation limited by availability of calibrator stars? From Jin Hake.
No, I think we can see I think we have calibrator stars for most of these systems. I don't think that's the main problem. I think it's really just some of the, like the binary parameter space. If the stars are too close together, if they're too faint, that's the main limiting factor if we can observe them. Is that what you mean?
Any more questions online or in person? If not, then let's thank Katie again.